Water boils in the pot. The glass beneath it stays cool enough to touch. There is no flame, no glowing coil, no heat creeping up from below. Yet the pan is searing hot, edge to edge, in seconds. Something is reaching up through solid glass and lighting a fire inside the metal itself. Nothing burns, nothing glows. So where exactly does the heat come from? Let us slice the cooktop open and watch it happen. Start with the stove, you know. A gas flame burns fuel and throws heat at the bottom of the pan. An electric coil glows red and does much the same. Both heat the air, the grate, and the whole kitchen, and only then the food. Most of that warmth simply drifts away. An induction cooktop throws all of that out. It never really gets hot on its own. Instead, it turns the pan into the heater. To see how, we go under the glass. Lift the smooth glass top and look underneath. There is no burner waiting. There is a flat spiral of copper wire, wound tight like a coiled rope, sitting just below the surface. This is the work coil. On its own, it does nothing at all. It does not glow. It does not warm. But feed it the right kind of electricity, and this quiet loop of wire becomes the source of everything above it. The first step is the current we send through it. The cooktop does not send plain household power into the coil. It chops it up. Electronics switch the current back and forth, reversing its direction roughly 20,000 times every second. That is far faster than the 50 or 60 cycles coming from the wall. Why so fast? Because a current that flips this quickly does something useful in the space around the wire. It builds an invisible field that pulses just as fast. That field is the real tool. Every electric current wraps itself in a magnetic field. Send the current racing back and forth, and that field grows and collapses right along with it, surging up through the glass and into the air above the coil. Glass does not block it. The field passes straight through, unbothered, reaching into the space where the pan will sit. You cannot see it, you cannot feel it on your hand, but set the right metal in its path, and the field has somewhere to push. Now lower a steel pan onto the glass. The pulsing field floods up into the flat metal base. And here is the trick. A changing magnetic field, pressing into metal, stirs the electrons inside it into motion. The field is reaching through the glass and grabbing the charges within the pan itself. It does not heat the pan from the outside. It reaches inside and drives an electric current deep in the metal without ever touching it. These stirred-up currents have a name: eddy currents. Picture water swirling behind a paddle. The electrons loop in tight whirlpools through the base of the pan, round and round, switching direction 20,000 times a second to match the field below. No wire connects to the pan. The current is born inside the metal, conjured by the field alone, and a current forced through metal cannot move freely. The metal fights back against it. Every metal resists the flow of electricity, even a little. As the eddy currents whirl through the pan, the metal drags on them, and that friction has to go somewhere. It turns into heat. This is the same reason a wire warms when too much current runs through it. But here it happens everywhere at once, throughout the whole base of the pan. The metal is not warmed from below. It cooks itself from the inside out. So the pan is the burner now. It glows with heat born in its own base, and that heat spreads up the sides and into the food. The glass underneath, it was never the source. It only warms by touching the hot pan resting on it. Lift the pan away mid-boil, and the cooktop is merely warm, not dangerous. The heat lived in the metal all along. That is why a spill on the glass does not scorch. Because the heat comes from electronics, control is almost instant. Turn the dial up, and the cooktop pushes more current through the coil, strengthening the field and the currents inside the pan. The metal heats harder at once. Turn it down, and the swirling eases within a moment. There is no glowing element to slowly cool, no flame to settle. The response is as quick as flipping a switch, because that is nearly what is happening. This is why some pans simply will not work. The field only takes firm hold of metals that are magnetic, like iron and most steel. Set down a pan of plain aluminum or copper, and the field slips through with little to grip. No eddy currents, and so no heat. There is a quick test. touch a kitchen magnet to the base. If it clings firmly, the cooktop can heat it. If it slides off, the pan will sit there cold. Step back and notice what never got hot. Not the air, not the glass, not the room around you. Nearly all the energy went straight where it was needed, into the metal holding the food. A flame may send half its heat past the pan and into the kitchen. Induction wastes very little of it. That is why a pot of water can come to a boil so fast it almost startles you. The heat had nowhere else to go. So follow the whole chain. Fast-switching electronics drive a current back and forth through a copper coil. That current raises a magnetic field. The field surges up through the glass into a steel pan. Inside the pan, it stirs swirling eddy currents. The metal resists them, and that resistance becomes heat. The pan cooks the food while the glass stays cool. No flame, no glowing coil, no waste. Just a field reaching through glass to light a fire in metal. An everyday cooktop, hiding a small piece of invisible physics. A field you cannot see, lighting heat you can. Next time the water boils on cool glass, you will know exactly what is reaching up to do it. We will see you in the next cutaway.